All right, well, welcome back, folks. Let's go ahead and let's continue on with where we left off with yesterday. I'm going to try to finish up with this background information and then hopefully start into the gas laws today as well. But let's go ahead and let's take a look at what we where we left off with yesterday. I want to finish up by using this FET here to help you with it, and then pick up from there. Okay. The main idea that I want you to take from these discussions here using the FET is that we want to be able to make that connection between microscopic, what's happening at the particle level, what the gas particles are doing, and what we can observe on a macroscopic level. So from the FET here, then we are able to see on a macroscopic level the measurements that we take here with our thermometer and with our pressure gauge here. And the readings that we obtain from the thermometer and from the pressure gauge is a direct result of what the gas particles are doing inside this chamber here. That's at the microscopic level. So what we need to be able to do is, if you can make that connection, then I think the understanding of the gas laws will become much clearer to you. You'll have a clearer understanding of the gas laws, because what the gas laws do is that they just relate for us. Relate for us the pressure and what we can see here. This is the observable event with what's happening on the microscopic level. Okay. All right. So we focused in on pressure yesterday, so please make sure you take a look at that. And the key takeaway then is that my hope then is you can see then that when we talk about pressure, okay, it's the gas particles. The gas particles moving, so it's the movement of the gas particles inside this chamber here. But more so, it's the movement and what leads what causes the collisions. The movement, obviously the particles have to move so that the particles can collide, but it's the collision of the particles with each other and the collisions of those particles with the whatever's in the gas chamber and the sides of the chamber and the pressure gauge itself that is what leads to this pressure gauge moving up. Okay, so that's what we saw yesterday. We saw yesterday then that as we added gas, so if you as you notice it, as soon as you add the gas, there it is. The pressure gauge starts to move up, the temperature starts to move up. Okay, we have a temperature now, and it's these gas particles here that are moving and colliding in with one another. Okay? And it's these collisions here that results in the pressure that we observe as we look at the gases here. Okay, so make sure you understand then that the link that you have to be able to make is the collisions between these gas particles here on a microscopic scale and the pressure that we read here on the macroscopic scale. Okay, and so the whole idea behind force and pressure, make sure you are okay with that. But again, the basic takeaway that I want you to get from yesterday is on a microscopic scale, it's the collisions of these gas particles here that leads to, on a macroscopic scale, the pressure that we can read here. Okay, all right. So that's how we can account for gas pressure. So the gas pressure then we can now explain it based upon the behavior of these gas particles. Okay? So let's continue on with our discussion. And I want to ask you this. Okay? At what point does does the pressure gauge here read zero? Well, let's consider this. Does it read zero or does it go down? Does it go down when we add more gas particles? Well, if I just added another gas, I doubled the number of gas particles from 50 to 100. You notice then that the pressure went up. Okay, so the pressure went up, and so the question then is, obviously, then the increasing the number of particles does not decrease the pressure. Okay, so what if we start taking away? Okay, all right. So I took half of it away. I took half of the particles away at that point. Okay, and then now I'm going to take the rest of it away. Well, look at that, folks. Okay. So what happens here then is, if you notice then that the pressure then changes with the number of particles. Okay, so if you notice here, as we decrease as the number of particles, so we decrease the number of particles. Okay, okay, what that leads to then is a decrease in the pressure. Okay, so that means then what we have here is that on a microscopic level, as the number of particles decrease, that leads to a decrease in the pressure as well. So that when the number of particles equals zero, when we have no particles, okay, the pressure, and if you see here, okay, equals 0.0 atmospheres. Okay, so Then we can see then that how can we create a situation? How can we create a situation in which the pressure is zero? Well, we take everything out of the, and I'm going to include this here, take everything out of the chamber. That means we remove everything from the chamber, and in removing everything from the chamber, we now have a situation in which the pressure is zero. Okay. What we can say here is this then, folks, what we've created, what we've just created inside this chamber here, what exists inside this chamber here, is what we refer to as a vacuum. Okay. A vacuum then, and let's go ahead and let's make sure we understand this. Okay. A vacuum then is defined then as as empty space. Okay. That means then there is nothing in this space here. Okay, no particles, no pressure. And so whenever you create a vacuum, okay, whenever there's a vacuum, make sure you understand this. Whenever there's a vacuum, we define that as a situation where it's the number of particles, and I just wrote this for you already. The number of particles is going to be equal to zero, so no particles, and the pressure then will also be equal to zero. Okay, so in that case then, this is how we define a vacuum, and a vacuum then, and it is a space. There's absolutely no particles at all. So with that said then, is there anywhere in the universe that represents a true and complete vacuum? The answer there is no. There's everywhere in the universe, even in deepest, darkest space, and there's still going to be remnants of something out there. There's going to be some type of particles out there, and as such, then we will see then that it's not a true vacuum. However, we do have certain situations where we can create a vacuum here on Earth. We have what's called a vacuum chamber, and we can go ahead and suck out all the air from that vacuum chamber. I have one in our class. Okay, and so with that said, then in that space for that particular moment, we have created a true vacuum in which then I've taken out all the particles, and as a result, the pressure inside that chamber is going to be zero atmosphere. Okay, all right, so that's in space. That's in a vacuum chamber. Okay, what happens then? And I'm going to go switch here really quickly, folks. Okay, so let me go ahead and bear with me. Okay, so I'm going to switch over to the slides. Okay, so with that said, then what happens then when we are here on Earth? Okay, what happens here on Earth? What is the pressure like here on Earth? Because obviously, do we have pressure on Earth? Well, first of all, the answer has to be yes. We have gas particles moving around. The Earth's atmosphere is made up of gas particles. Okay, and so think back to what we did with the PhET lab there. If you can imagine the Earth then as being that chamber. That chamber then is filled with gas particles. Okay, and so the Earth that we do have pressure here on Earth. As long as we live here on Earth, there is this pressure, and we refer to that pressure then as atmospheric pressure. The reason for that then is that the Earth's gravitational force pulls these gas particles down in much the same way we are pulled down towards the surface of the Earth through the force of gravity. So the same force of gravity that holds us down and holds us to the ground and pulls us down to the ground is also pulling down on the gas particles as well. So if you want to think about it, you can think of the Earth as one big balloon or one big gas chamber, okay, that is filled full of gas particles. And remember, these gas particles are in constant, random, rapid motion. That's the kinetic molecular theory. And as they move around, they collide, and those collisions lead to gas pressure. And so on Earth here, we feel this pressure, okay? And I'm sorry, we don't feel it on a daily basis, but let's say then you go up into the mountains. You definitely feel that there's a change in the atmospheric pressure, and we'll talk about that in just a moment. Okay? But there is that pressure there, okay? And so how then can we imagine what atmospheric pressure is? Okay, well, or how we can imagine the changes in atmospheric pressure? Well, let's consider what we have here. Okay. Atmospheric pressure changes. The atmospheric changes with your location. Now, as long as we are here on the close to the ocean here, whether you are up in Torrance or wherever you're at, we're still roughly at sea level. Okay, so at sea level, then we feel a certain pressure. Okay, and that pressure then doesn't change, so our body adapts to it. Okay? However, you notice a significant change. So if you've ever been up to the mountains, you've noticed then a significant change, and I'm just going to draw a line right here. As you move up in elevation. Okay, so as you go up in altitude, so altitude increases as you go up here. So as you go up in altitude, you start feeling that change in the pressure. Your ears start to have to, you start feeling the tension in your ear. Okay, and so that's a result of a change in atmospheric pressure. That's a change in atmospheric pressure. So as you move up, the atmosphere changes. And so the question then is, as you move up in altitude, so altitude, that is the elevation, as you go up in altitude, so this is sea level here, you can imagine sea level D at the base of the mountain here, and as you move up towards the top of the mountains, you are increasing the altitude. What happens to the pressure as you move up? Okay. Well, I'm going to, so first of all, we see here then, and I'm going to highlight this for you, see then that as you go up in atmospheric pressure, okay, as you go up in elevation, okay, as you increase your elevation, okay, the atmospheric pressure here, the pressure itself decreases, okay, and so what we have here then, let's go ahead and write this down, what we have here then as what this is saying here then, as you go up, as the altitude increases, that corresponds directly, so this is proportional to a decrease in the atmospheric pressure. And that is what this statement, and that's what I need you to make the connection on. Okay, so how can we imagine this? So make sure you understand that what this is telling us then is that as you move up in elevation, as you go up a mountain, actually the pressure is decreasing. And you probably have heard that term mentioned before, that the air up in the mountains is thinner. So you have thinner air up here. Okay, so what does that term mean? Well, I want to draw this, to get you to understand this then, I want you to try to imagine what happens when you go swimming. Okay, when you're swimming out of the ocean, or you're swimming in your pool, or in a pool, okay? So let's imagine this then, that here you are, so let's imagine this is being a pool. So here you are swimming at the top. You are at the surface of the pool. Okay, there you are. You're at the surface of the pool, and then you dive down. Okay, you dive down into the water itself. Okay, and so what you'll notice in this, at the bottom here, when you are at the bottom of the pool here, okay, you can imagine that the pressure is pushing in on you. You can feel that. You can feel it on your ears as well. The pressure is pushing in on you. And the way you can imagine this is that up here, you don't have as much water surrounding you. You have less water surrounding you at the top here. You only have the water surrounding you at the top of around your body here. But when you get down to the bottom of the pool, you have a lot more water. There's more water pushing in on you. Okay, so more water equals more pressure. That's how you want to try to imagine this. You have less water up here, more water down here, less water particles up here, thus less pressure. You have more water particles down here, means then you have more pressure. If you can remember that, and let me go ahead then, let's draw this back to the situation here with the altitude, okay, and the air, okay. So we said that at the top of the mountain here, the air is thinner. We have thinner air at the top. And exactly what does that mean? We have thinner air means then less air particles. Okay. Less air particles, okay, and you have more air particles down here. Again, think of the water. Less water particles up here at the surface of the water, more water particles down here at the base of at the bottom of the pool. Okay? Less air particles at the top here, more air particles at the top here, which means more air particles at the bottom of the mountains here, which means that at the bottom of the mountain, which is at sea level, you have more air particles, which means then the pressure down here. So this is the pressure down here, we'll call this pressure 1, is going to be greater than the pressure at the top. Okay, so pressure then at sea level is going to be greater than pressure at higher altitude. So as you move up in altitude, the pressure decreases. That is unlike the water, whereas you go, I'm sorry, so that is almost identical to what we have with water. So as you go up the water, as you ascend then the water, as you swim back up, you feel less pressure. So this is exactly the same situation as with water. And that's how that's what you can use to to understand what this summary is right here. So as you go up in altitude, the atmospheric pressure decreases. Okay, so you want to make sure you keep that in mind as we move forward with it. Okay, all right. So so with that said, then can we measure? Is it possible to measure this atmospheric pressure? The answer is yes. We can measure the atmospheric pressure using different tools. We have different gauges that we can use to measure pressure. But the idea here is going to be basically the same as what we have here. Okay, so this is what's called a mercury barometer. Okay, this is a mercury barometer. Okay, and this barometer basically works by taking a what you have here is a dish full of mercury. Okay, and then you take a test tube here that's marked off with in increments of millimeters. Okay, so each tick mark here represents a millimeter of space. Okay, so you have a distance here of 1 millimeter. Okay, so you tick off this test tube here. Okay, okay, and what you do then is you fill it with mercury, and then you flip it upside down and you put it inside this dish here. Okay, all right. The mercury is a metal. It is a metal, and it's remember the only metal that's in the liquid state. So it's a dense liquid. Okay? And so therefore it's going to get pulled down by gravity. Okay, but at some point it's going to stop. When you flip it over, it's going to stop. Why? Because what happens is the mercury outside here is also experiencing pressure. The pressure then from the air pressure pushes down on this mercury, the dish of mercury here, and that's what prevents the column here from sliding down any further. So at this point here, when the mercury stops moving, there's this balance between the gravity pulling down on the mercury column and atmospheric pressure pushing up on the mercury column itself. Okay? However, if you take this barometer here and you move it up into the mountains, the air pressure drops. You have less air pressure, and so I'm going to ask you to do this really quickly. Answer this question. If the air pressure drops, will this mercury column go down or will it go up? So take a couple of seconds, type that into Edpuzzle. Okay, type your answer into Edpuzzle, and then we'll talk about it. Okay, so take 30 seconds. Go ahead and type in your answer. Okay, well, let's consider this then. You have less air pressure outside pushing down on the mercury here. Okay, and remember the mercury column here is being pushed down by gravity. Gravity is pushing down on it. Okay, and so if you have less air pressure here pushing down and thus pushing mercury into this column here, pushing it less pressure pushing up, gravity wins. Therefore, the column goes down. And so therefore, when you take this mercury barometer up into the mountains, you're going to see then that mercury column is going to drop to a lower level. Okay, so the mercury level goes down, the pressure as a result of the pressure going down. Okay, so that's the really cool, simple thing with this mercury barometer here. And you don't really typically see mercury barometers anymore because the mercury is fairly dangerous to work with. Okay, but with that said, then you can measure the column here in millimeters of mercury. Okay, so you can measure the drop in millimeters of mercury, and so this is and this represents then a unit of pressure that we can use. Meteorologists, and many of them still use it. They also use kilobar and millibar as a unit of barometric atmospheric pressure as well. And you can go on the Weather Channel, you can see that. Okay, they'll also use inches of mercury as well. Here in the United States, we use the imperial system, so you'll see that inches of mercury as well. Okay, all right. So with that said, then we can measure the atmospheric pressure now using this mercury barometer in millimeters of mercury. Okay, but actually the SI unit, the unit for pressure then is the pascals, and actually you'll see this this pressure unit in kilopascals rather than pascals itself. Okay, so with that said, other units that are millimeters of mercury and with atmospheres, and there's this relationship that we can take advantage of in terms of conversions between each one of those units, and it's given to you here. Okay, and so the only what you'll need to be able to do for our work here and the work that we'll be doing moving forward with the gas chapter then is being able to convert these units here and work them out. Okay, so let's go ahead then. Let's do a problem here really quickly together. Okay, I just want to work this one out with you. Okay, and I want to show you how to do it. Okay, all right. So with that said, then the conversions here are pretty straightforward. You just have to make sure you identify what the conversion is. Okay, so remember with all conversions, you identify what you start out with, and so we're starting out with 450 kilopascals here, and they want you to change that into atmospheres and millimeters of mercury. So there's two conversions that you want to do here. Let's go ahead and do both of them. Okay, so starting then with 450 kilopascals. We want to convert that into atmospheres first. Let's go ahead and do that. The conversion factor based from the previous slide then is going to be then, and let's go ahead and plug it in. Okay, 1 atmosphere over 101.3 kilopascals. Okay, and so let's real quick plug that into your calculator. So 450 divided by 101.3, okay, and you end up here with an answer of 4.44 atmosphere. Okay, all right, doing the same thing then for the millimeters of mercury. We're going to start out then with 450 kilopascals. We're going to convert that now into millimeters of mercury. Okay, and the conversion factor we're going to use here, based upon the relationship we saw in on the previous slide, is going to be then 760 millimeters of mercury, okay, over 101.3 kilopascals. And putting that into our calculator, let's go do that really quickly. Sorry, 450 times 760 divided by 101.3, we get then 3.4 times 10 to the third millimeters of mercury. I'm sorry, millimeters of mercury. Okay. All right. So that's what we have here. Okay. And yeah. Okay. And so let's go ahead then. What I'd like you to do is I want you to go ahead just to finish out here. Okay. I want you to work through this problem here. So that real quick, take a look at this problem. Let's work through this and then take about 5 minutes to work on it. And then when you get back, we will go over this together. Okay, so go ahead. Let's work on this particular problem here. And let me look at something real quickly. Okay. And then let's go over together. Okay, so take 5 minutes. All right. Let's take a look at this problem here. Let's work this one out together. Okay, and let's real quickly this time let's identify what we're given. And I'm running a little over here, so apologize for that. But let's go ahead and finish this. All right, so we're starting out here then with 75 kilopascals. Okay, and let's do the first conversion. They want us to convert it to millimeters of mercury and to atmospheres. Let's go ahead and convert it to atmospheres first. Okay, and so doing the same thing then, we're gonna have 1 atmosphere over 101.3 kilopascals. Okay, so if you plug that in, then you'll get your answer there. It's being 0.740 atmospheres. Okay, and then the second conversion then is 75 kilopascals. We're going to convert that into millimeters of mercury, which is going to be 760, like we did in the previous one. 760 millimeters of mercury over 101.3 kilopascals. Okay, as our conversion factor. You plug that in, then you get 563 millimeters of mercury. Okay. All right. So let's practice that a little bit more. I'm going to assign the homework for tonight so you can get done. So let's practice this a little bit more. What I'd like to do tomorrow then is finish up with our discussion here. I'm going to go over just a couple of the gas laws. I don't think we'll be able to go through all of them. And then we'll finish up the semester on Friday, and we'll meet at that point. Okay. All right. Very good, folks. Have a good day, and I will see you on. I'll see you tomorrow.